Welcome back, everybody. In the last video and section we talked about double integrals over rectangles, but we also want to be able to integrate over more interesting regions than just a rectangle. So in this section we're going to talk about how you can evaluate double integrals over general regions in the XY plane. So the idea is we want to find the volume of a solid that might look something like this, right? So we have some strange looking region in the XY plane, and we evaluate some function at all the points in that region, so we get some kind of surface, and then the double integral of this function over this region gives us the volume of this solid. Now, to begin with, I'm going to just be examining how we can describe this region in the XY plane. Because when we were integrating over rectangles, right, it was pretty simple. We just integrated from A to B in the X direction, integrated from C to D in the Y direction, and that gave us the integral over a rectangle. And that's still the case. If we just integrate from A to B and C to D, that gives us the integral over a rectangle. But now we don't want the entire rectangle. We just want this region inside the rectangle. So we need to come up with other ways than just integrating between numbers. We need to come up with a way of describing the boundary of this region so that we only integrate here and not over a rectangle. And so just like with integrals over rectangles, we can set up these integrals in two ways. And so the first way I want to describe integrating over this region is by integrating with respect to y first. So we have some integral over some region that I'm going to call d of a function, f of xy. I'm integrating with respect to y, and then I'm integrating with respect to x. And I want to see how I can describe this region so that I can actually come up with bounds and integrate. So if I want to integrate with respect to y first, then I want to think of adding things up in a y direction. So I'm going to start talking about either moving vertically for y or horizontally for x. And integrals we can think of, or at least the way I think of it, is a continuous sum. So if I'm integrating in a y direction, I'm adding up these function values vertically. So if I'm integrating with respect to y, I'm thinking of this region vertically. And I want to find a way of describing where I'm always starting and where I'm always stopping. If I want to stay in this region, and let's just pretend these are the same region, I tried to draw them the same, then I want to find this curve that describes the bottom of this region. That's where I'm always starting if I think vertically. I'm always starting at this bottom curve, and I'm always stopping at this top curve. So I need to find ways of describing these two curves, and then say, okay, I'm going to integrate in the y direction, always starting at this bottom curve, and always stopping at this top curve. Now, once I do that, if I'm adding up all these function values, you can think of a function value as a length, right? For each individual function value, I get some height, which has a length, you can think of it. So in the y direction, I'm adding up all these lengths. For any given value, if I add up a bunch of lengths, I get an area. So once I integrate in a y direction, what I'm left with are a bunch of cross areas of this solid. So once I have all the cross areas of this solid, basically the region is dealt with, and I just need to add up these cross areas in an x direction, and I get the volume. But when I add up these cross areas, the cross areas themselves take the region into account. So when the second integration I do, I just need to integrate from A to B, the leftmost point to the rightmost point. I add up all these areas. So I'm integrating these areas that I've already gotten by integrating in y, and I get the volume. So to summarize everything I just said, now with more written details, I can describe this region by bounding my y variable between two functions of x. So some g1 of x is the lower bound, this red curve. g2 of x is the upper bound, this blue curve. And say, okay, those are my bounds for y. And in x, I'm just going to keep these numerical bounds, okay? Because these curves take care of the boundary of the region. and I say, okay, if y is always between these two curves, that gives me the shape of my region, and then I can just let x go from one value to another. So that gives me, when I set up this integral, that y is bounded by two functions, g1 and g2, not just c and d, and I can describe this integral as the integral in y from g1 to g2, these are functions of x, and then an x, an integral from a to b. That's one way to set it up. A second way to set this up is by integrating with respect to x first. If I want to integrate with respect to x first, I want to start thinking of how I can be bounded in this region in a horizontal way. Because if I'm integrating with respect to x first, I'm moving horizontally. So I start thinking of terms of moving from left to right. So if I'm integrating with respect to x, I'm moving from left to right, and I want to know, okay, what is a curve where I'm always starting with on the left, and where's a curve where I'm always stopping on the right? So I always look left to right, and so I want to find the leftmost curve, that's going to be some function of y, and the rightmost curve, also going to be some function of y. And I see that if I'm moving in this region horizontally, I'm always going to be starting at this h1y, what I'm calling h1y, this red curve, and I'm always stopping at this blue curve, h2y. It's the same region, now I'm just thinking horizontally instead of vertically. So I can describe this region as all of the x values bounded between h1y and h2y. And then I can just let y go from c to d. Because these curves are the boundary of my region, they take care of describing the shape of my region. And then y can just be, okay, once I have all the x values inside this region, I just need to know where am I starting and stopping with y. And that can describe all the points of my region. So then I set up the integral this way. If I integrate with respect to x first, I'm integrating from some function of y to another function of y that describes the boundary of my region. And then in y, when I integrate, I just go from c to d. So these are numbers. In the end, I want my answer to be a number. So my last set of bounds have to be numbers. And again, you can think of, I have all these single function values. At every point I have a function value. I add these values up. You can think of them as a length. I add all these lengths up in an x direction. I integrate in an x direction. That gives me an area. A bunch of lengths together give me an area. So now I have all these cross areas of my solid. And if I integrate in y, I'm adding up all these cross areas to give me a volume. And so that's one way you can think of it. We also have Fubini's theorem for general regions. I haven't written this down, but what I have here kind of summarizes it. This is the same integral. I've just written it two different ways. So for Fubini's theorem, it says you get the same answer if you integrate with respect to y or respect to x first. It's the same thing here, but I need to put in some more work to change the order of integration. For rectangles, I could just switch x and y and switch the bounds and everything was fine. But here I can see that's not the case. If I switch integrating with respect to x and y first, I don't just switch my bounds, because my inner set of bounds are functions, so they go from being functions of x to functions of y, and my outer bounds are numbers. So this AB doesn't become AB here. It becomes two functions that describe my region. And then I don't need these two functions anymore because I have two different functions describing my region, and I get C and D. This will make sense once we do some more examples, but just so you know, we also have Fubini's theorem for general regions, but it's not as simple as just switching a set of numbers like it was for rectangles. Okay, let's look at an example. So first, ignore all of this for a second. This is the example that I'm giving you. It's an integral that's already set up. I want to integrate the function 3y, and the x bounds that I have, I'm going from a function of y, 3y squared minus 6y, to another function of y, 2y minus y squared. So these are two curves that are bounds for the region I'm integrating over. Okay? And then my y bounds, I'm just going from 0 to 2. So if I integrate this, I integrate with respect to x first, so I can think of this 3y as just a constant. So when I integrate, I get 3xy, but now I'm evaluating from one function to another function. So when I plug in my bounds of integration, I get 3y times I need to plug in 2y minus y squared into x. So I get 3y times 2y minus y squared minus 3y times another function I plug in for x, 3y squared minus 6y. So already this is more complicated, right? I'm plugging in these functions instead of just having numbers here. But from here I can simplify this. And this is just some algebra. I distribute the 3y. I distribute here, that gives me 6y squared minus 3y cubed. I distribute this minus 3y, that gives me minus 9y cubed plus 18y squared. Now I can combine like terms, and that's going to give me 24y squared minus 12y cubed. And now I just have an integral with respect to y, and I have a function of y. At this point, you shouldn't have any x's. Once you've integrated with respect to x, you've plugged in your bounds, all of the x's should be gone. If you get to this point and you still have two variables, you have x's and y's, something has gone wrong. You need to look back at your work and see what happened. Because now I should just have a function in one variable. And this is just an integral like you would have seen in Calc 1 or Calc 2. So now I continue to integrate this with respect to y. And I'm going to get 8y cubed minus 3y to the fourth, evaluated from 0 to 2. So 2 cubed is 8, so that's 8 times 8. 2 to the fourth is 16, minus 3 times 16. I plug in 0, I get zeros. So that is 64 minus 48, my answer is 16. We still want our answers to be numbers. So if you finish your second integral and you have variables here, for these kinds of problems, there's something wrong. Your final answer should be a number. Okay. Before we move on, there's some things I want to point out about this example. The first thing I want to point out is that we can still pull constants out of these integrals. So I could have started, since I was integrating 3y, I could have pulled that 3 out and just integrated y. That's fine. I don't know if that would have saved us any work. I would have had, at some point, a 3 out here, all the way down, and then I would have had 3 times probably some fractions in here in order for me to get 16. So there's nothing wrong with that. We can't switch the order of integration, so this is what I was saying earlier when I was talking about Fubini's theorem. We can't just switch the order of integration without having more information about our region, right? So if this is our integral, I can't just switch my bounds and say, okay, I'm going to integrate with respect to y first. Because what's going to happen? If I integrate this with respect to y, I think if you do this integral, you get 6. So then I would be integrating 6 with respect to x. So I'd get 6x, and then I plug in these two functions for x, and I would have a function of y as my answer. I don't want a function of y as my answer. I want a number as my answer. So you can switch the order of integration if you know more about your region, and you can, instead of using 0 and 2 here, I can describe my region as two functions of x, and then these become numbers. But for this example, we don't know more about our region, so this is as much as we can do. And then the last thing I want to point out is that I can't separate this integral. And sorry for this mess. This is actually the beginning of the next video. But anyway, looking at this, I can't separate this integral like I talked about in section 15.1, where we said, okay, I can think of this as 3y times 1, where 3y is a function of y, 1 I could think of as my function of x. So can I just write this as an integral in terms of y times an integral in terms of x? No, this doesn't work for the same reason switching the order of integration doesn't work. Because if I evaluate this integral, I still get, I think it's 6, whatever I said this was. And if I evaluate this integral, I'm going to get a function of y. I'm going to have y's in my answer. So for these, if you have variables in your bounds, you have to actually do integrate with respect to one variable and then the next variable. You can't separate it like we could in the last section. Okay, one of the most difficult things about these kinds of problems is setting up the integral. So in this example, the integral was set up for us. All we had to do was integrate. But in the next video, we're going to do examples where we're just given a region and we have to set up the integral ourselves.